You look up at Saturn. Those rings, bright, clean, icy halos wrapping a gas giant. But here's what nobody tells you. 4 giants in our system wear rings. Jupiter hides them in dust. Uranus stacks them like dark ribbons. Neptune strings clumpy arcs that shouldn't exist. And past them, out in the frozen belt, an asteroid the width of 300 kilometers spins with 2 icy loops nobody saw coming. Rings aren't rare. They're everywhere. The question isn't who has them, it's why each set breaks every rule we thought we knew. If you value documented planetary science and deep space discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Nature Geoscience's December 2024 study on micrometeoroid impact resistance, published by Ryuki Hayoto at the Institute of Science, Tokyo, and the monthly notices of the Royal Astronomical Society. January 2024 analysis of Saturn's E-ring composition by Len Snola at the Cosmic Dust Analyzer team. These aren't pop science summaries. These are direct peer-reviewed findings, cross-checked with Voyager imaging data, Cassini's 13-year orbital mission results ending 2017, and James Webb Space Telescope's 2022 Neptune ring observations. Now back to the information. March 4th, 1979. Voyager 1 aims its camera at Jupiter's equator. The mission team told engineers to look: 1 overexposed 11-minute exposure. A faint band crosses the frame, 57,000 kilometers from Jupiter's cloud deck, 30 kilometers thick. The ring nobody predicted because Jupiter's massive moons should rip it apart. Voyager found it anyway. 3 days later, Mauna Kea confirms it from Hawaii. Jupiter's ring isn't ice, it's dust. Microscopic fragments kicked off 4 tiny moons: Metis, Adrastea, Amalthea, Thebe. High-velocity meteoroid impacts blast material into orbit. The main ring stretches 6,000 kilometers wide. Inside it, a halo clouds upward. Outside, 2 Gossamer rings spread to Thebe's orbit. The dust doesn't last. Radiation pressure, atmospheric drag, electromagnetic forces from Jupiter's magnetic field sweep particles into the planet within 1,000 years. The ring survives because impacts keep feeding it. A conveyor system. Break, drift, fall, replace. Galileo spacecraft confirms the source in 1998. Cornell's Joseph Burns identifies the supplier moons from trajectory analysis. The ring is temporary, but it's always there. Saturn, 282,000 kilometers of ring-span edge to edge, 99.9% water ice. The Cassini mission measures ring mass in 2017 during its grand finale orbits, 1.54 times 10 to the 19th kilograms, about 40% the mass of Saturn's moon Mimas, spread across 80 times Earth's surface area. The ice particles range from micrometers to 10 meters. Most are a few centimeters. The main rings, A, B, C, split into thousands of ringlets. Giovanni Cassini finds the big gap between A and B in 1675. Cassini division, 5,800 kilometers wide. Not empty. Voyager, 2 images in 1981 show faint ringlets inside. The gap exists because of Mimas. Any particle there completes 2 orbits for every one Mimas orbit. 2-to-1 resonance. Repeated gravitational tugs at the same orbital point destabilize particle paths. The division clears. The outer edge of the A ring sits at a 3-to-2 resonance with Mimas, sharp edge, controlled by gravity math. The F ring orbits 3,400 kilometers beyond the A ring's edge, narrow, multi-stranded. Discovered by Pioneer 11 in 1979. Prometheus and Pandora patrol it. Shepherd moons, they're called. Prometheus orbits inside, Pandora outside, each about 100 kilometers across. Their gravity confines the F ring particles. Prometheus periodically plunges into the ring, drawing streamers and fans. The interaction is chaotic. Both moons' orbits wobble in overlapping 121 to 118 mean motion resonances with each other. Every 6.2 years, their orbits align in ways that shift their paths. Cassini tracks this for 13 years. The F ring shouldn't be stable. It is, because collisions and electromagnetic forces create a dense core trapped in corrotation eccentricity resonance with Prometheus. Chaos breeds structure. Saturn's E ring is different, massive, diffuse, stretches from Mimas' orbit past Rhea, 700,000 kilometers wide. Fed by Enceladus, August 28th, 1789. William Herschel discovers the moon. Voyager 1 in 1980 shows a young, crater-free surface. Cassini arrives 25 years later, finds plumes, water geysers erupting from tiger-stripe fractures at the South Pole, 200 kilograms per second launched into space, ice crystals, sodium chloride, organics, molecular hydrogen, The plumes shoot out at 2,189 kilometers per hour. Some falls back as snow. The rest escapes, becomes the E ring. Cassini's cosmic dust analyzer samples the grains. Lenz Nola's team identifies 5 particle types in 2024. Type 3 particles, salt-rich ice from Enceladus. Type 5 particles, extremely salt-rich, formed when plasma sputtering strips away the ice component from type 3 grains between Dione and Rhea. Space weathering in action. Photochemical degradation converts organics into volatile fragments. The ring evolves as particles migrate outward. Without Enceladus feeding it, the E-ring dies in 10,000 to 1 million years. Right now, it's alive. Saturn's rings are young, or they're not. Cassini measures incoming micrometeoroid flux. Non-icy material bombards the rings constantly, 0.69 to 2.7 times 10 to the minus 16 kilograms per square meter per second. Traditional models say that darkens the ice over time. The rings look clean, therefore young, 100 to 400 million years old. December 2024, changes that Ryuki Hyodo at the Institute of Science Tokyo runs simulations. Hypervelocity impacts vaporize incoming silicate material. The vapor expands, cools, condenses into charged nanoparticles and ions within Saturn's magnetic field. They don't stick, they collide with Saturn, get dragged into the atmosphere, or escape. Pollution efficiency drops below previous estimates. The rings stay clean even if they're billions of years old. The appearance doesn't date them. The structure might, or might not. The age question reopens. March 10th, 1977. James Elliott, Edward Dunham, Douglas Mink fly the Kuiper Airborne Observatory over the Pacific. Watching Uranus pass in front of star SAO 158687, stellar occultation. The star dims 5 times before the planet blocks it, dims 5 times after, same intervals. Rings, narrow, sharp-edged, spaced. 5 rings confirmed that night. More found later. 10 total by Voyager 2's arrival January 24th, 1986. Named inward from Uranus, 6, 5, 4, Alpha, Beta, Eta, Gamma, Delta, Lambda, Epsilon. The cumbersome names come from discovery order. They don't fit a pattern. Uranus rings are dark. Albedo near 0.05, blacker than coal, mostly carbon and hydrocarbon compounds. Tholins, the kind found on asteroids, comets, Uranus's inner moons. The particles are large, bigger than 140 centimeters in most rings. Little dust in the main rings, but dust fills the gaps between. The dust lifetime is short. Atmospheric drag. Radiation pressure from sunlight kill dust orbits in 1,000 years. Collisions create it constantly. The rings themselves may not last. Atmospheric drag is large. The rings might be spreading, slowly dying. Shepherd moons stop the spread. Cordelia and Ophelia bracket the Epsilon ring. 2,000 kilometers inside, 2,000 outside, about 50 kilometers across each. Their gravity confines the particles, but theory says more shepherds should exist. Voyager didn't find them. They might be there, too small to see, or the confinement works differently. No one knows. Epsilon is the brightest Uranian ring, reflects 2/3 of all ring light, varies in width from 20 to 96 kilometers. Eccentric orbit, the ring particles move in ellipses, not circles. Delta ring has a narrow core and a wide dusty component. Lambda ring is pure dust, detected by Voyager in ultraviolet occultation. Hubble and Keck telescopes image the rings from Earth after Voyager. Adaptive optics reveal fine structure. The rings precess under Uranus's oblateness. Gravitational resonances with moons perturb them. Perturbations appear to vary with true anomaly. Lindblad resonance is suspected. The rings may be primordial, formed with Uranus 4.6 billion years ago, or they're young from a shattered moon. The Roche limit for Uranus sits at 0.06 Uranian radii. All rings orbit inside or near it. Tidal forces prevent particles from sticking together. They orbit as rubble, forever. Neptune. 5 main rings: Gal, Leverrier, Lassell, Arago, Adams. Leverrier is narrow, 110 kilometers wide. Lassell spreads 4,000 kilometers. Adams is the star. It holds arcs, bright clumps embedded in a faint continuous ring. Fraternité, Égalité 1, Égalité 2, Liberté, Courage. The names echo the French Revolution. André Braich's team proposes them. July 22nd, 1984. Stellar occultation. Patrice Boucher, Reinhold Hafner, Jean Manfroy at La Silla Observatory in Chile watch a star blink before Neptune covers it. Extra dips in brightness. Partial ring suspected. August 22nd, 1989. Voyager. 2 photographs of the truth. Complete rings. The arcs are dense regions in the Adam's ring. 5 arcs span a 45-degree segment, leading to trailing courage, liberté, égalité. 1, égalité 2, fraternité, range from 1,000 to 10,000 kilometers long. Galatea, a moon orbiting just inside Adams, provides gravitational confinement, 42 to 43 resonance traps, particles temporarily, but collisions should spread them in months. The arcs stay put. 30 years later, Hubble, Keck, James Webb Telescope in 2022 all see them. Still there, but fading. Imke de Peyter's team at Keck finds the Liberté arc degrading. At current rates, the arcs vanish in a century. The Adam's ring may be very young. A recent moon breakup, perhaps a few thousand years ago, or the confinement mechanism is stronger than models predict. The arcs remain a puzzle. Neptune's rings are dusty. The Galilei ring, innermost, sits inside Moon Naiad's orbit, 42,000 kilometers from Neptune, pure dust. Leverrier, narrow and dusty, lies 700 kilometers outside Despina. Despina acts as shepherd. Lassell, the widest eye, extends 4,000 kilometers. Its bright outer edge is called Arago. Material throughout Neptune's rings scatters sunlight poorly. Dark, low albedo, dust dominates. The composition likely mixes ice and rock. But spectroscopy from Voyager and later observations can't nail it down. The ring system mass is tiny, less than any other giant planets. The rings are ephemeral. Voyager finds them anyway. Now small bodies, June 3rd, 2013, Chariklo. A Centaur asteroid orbiting between Saturn and Uranus passes in front of star UCAC 4248-108672. 7 telescopes across South America watch. The star blinks multiple times before and after Chariklo blocks it. Rings. 2 of them. 386 and 400 kilometers from Chariklo's center, 6.9 kilometers and 0.12 kilometers wide. Felipe Braga Ribas leads the analysis. The team nicknames them Oiapoque and Chuí, after Brazilian rivers. Chariklo itself is 250 kilometers across, largest known centaur. The rings are narrow, dense, icy. Provisional models suggest shepherd moons, but none are seen. Alternative theories propose Chariklo's elongated shape and fast rotation create Lindblad resonances that clear equatorial material and stabilize the rings. The rings should disperse in millions of years. They exist, young or confined. Pick one. January 21st, 2017. Haumea, a dwarf planet in the Kuiper Belt, passes in front of star Urat 1533-1182543. Jose Luis Ortiz's team coordinates 12 telescopes across 10 observatories. The occultation shadow projects Haumea's shape at full size onto Earth. Haumea is elongated, 2,300 kilometers long axis, minimum, spins every 4 hours. Fastest large object in the solar system. The occultation shows extra dips, a ring, 70 kilometers wide, 2,287 kilometers from Haumea's center. Opacity 0.5. The ring plane matches Haumea's equator and the orbit of its moon Hi'iaka. The ring sits near 3-to-1 resonance with Haumea's rotation. Well inside Haumea's Roche limit, about 4,400 kilometers. Tidal forces prevent ring particles from forming moons. The ring survives. First ring found around a trans-Neptunian object. Haumea's shape suggests a massive ancient collision. The ring may be debris from that event, or from a later impact. The discovery opens Kuiper Belt ring science, 2018 to 2021. Stellar occultation campaign on Quaoar. Trans-Neptunian object, roughly 1,000 to 110 kilometers across. Multiple ground telescopes and ESA's Chaops space telescope watch Quaoar cross distant stars. The observations reveal a ring, but this ring breaks the rules. It orbits at 4,000 kilometers from Quaoar's center, 7.4 Quaoar radii, far outside the Roche limit, which sits at 1.7 radii. Dense rings aren't supposed to exist there. Gravity between particles should pull them together into a moon within decades. Quaoar's ring is dense, optical depth around 0.4 in places. The ring is there, published in Nature 2023. Bruno Morgado leads the analysis. Theories scramble. Maybe Quaoar's moon, Waywatt, 80 kilometers across, stabilizes the ring through resonance. Maybe unseen moonlets. Maybe the ring particles are unusually bouncy, colliding without sticking. Maybe the ring formed very recently and we're seeing it mid-coalescence. Further observations in 2023 find a second inner ring. Quaoar has 2, both outside, where theory allows. The Roche limit rule bends. September 2023. Chiron, another centaur, 180 kilometers wide, occults a distant star. Brazilian astronomers detect brightness variations, suggesting rings. Chiron is small. If confirmed, it's the smallest ringed object. Chiron shows cometary activity, unlike Chariklo. Dust production, possible jets. The ring hypothesis competes with coma explanations. Earlier observations from 2011 hint at ring structures. Jose Luis Ortiz's team reanalyzes the data. Ring features match. Chiron might wear rings and coma together. The object straddles the asteroid-comet boundary. Rings would add another layer. As of 2025, Chiron's rings remain tentative. More occultations needed, but the pattern holds. Small bodies in the outer system wear rings. 3 confirmed: Chariklo, Haumea, Quaoar. 1 probable: Chiron, all discovered since 2013. The revolution is 12 years old. Why do rings form? 2 paths. The breakup hypothesis says a moon ventures inside the Roche limit or gets smashed by an impactor. Tidal forces or collision energy shatter it. Fragments disperse into a disk. The accretion hypothesis says ring particles never formed a moon in the first place. Leftover material from planet formation, trapped inside the Roche limit where self-gravity loses to tidal forces. Evidence supports both. Saturn's E ring is clearly fed by Enceladus, active source. Jupiter's rings come from meteoroid impacts on moons, temporary material. Uranus and Neptune rings might be remnants of destroyed moons, or captured comets ripped apart. Or primordial disks that never coalesced. The small body rings, Chariklo, Haumea, Quaoar, likely formed from collisions. Their parent bodies are too small to have leftover formation disks, impact debris scattered into orbit, then confined by rotation, resonances, or shepherd moons. Each ring system tells a different story. The one rule is no rule. Rings happen where gravity, collisions, and orbital mechanics intersect. Every intersection looks different. Shepherd moons carve gaps. Pan orbits inside the Encke gap in Saturn's A ring, 35 kilometers across. Pan sweeps particles from the gap, maintains sharp edges. Daphnis does the same in the Keeler gap, 8 kilometers wide. The moon creates rippling waves at the gap edges as it passes. Gravitational perturbations propagate through the ring. Atlas orbits at the outer edge of the A ring. Used to be called the shepherd of that edge. Turns out the 7-6 mean motion resonance with Janus does the work. Atlas just orbits nearby. Chaotic orbit, driven by 54 to 43 resonance with Prometheus. The shepherd metaphor breaks down under close examination. Prometheus and Pandora don't neatly herd the F ring. They stir it, create chaos, draw out streamers. The ring persists despite them, not because of them. Shepherding is a convenient story. Reality is messier. Gravitational resonances dominate. Collisions damp eccentricities. Electromagnetic forces add perturbations. Moons add complexity. The rings survive the chaos because they're made of billions of particles, each responding independently. Averaging over collisions produces order from chaos. Resonances stack. The Cassini division's inner edge is a 2-to-1 resonance with Mimas. Particles there complete 2 orbits per Mimas orbit. Repeated tugs pump up eccentricity until particles collide with material in adjacent regions or get ejected. The division clears, but it's not empty. Lesser resonances with other moons create faint ringlets inside. The Huygens gap in the Cassini division exists because of an 8-to-6 resonance with Mimas. Multiple resonances overlap. They create a mesh. Particles trapped in stable zones orbit between the gaps. Particles in unstable zones leave. The ring structure emerges from resonance geometry. Every moon adds resonances. Small moons add weak ones. Large moons add strong ones. Mimas, though small, orbits at the right distance to dominate several key resonances. Janus and Epimetheus co-orbit, swapping positions every 4 years. Their combined resonances shape the outer A ring. Tethys and Diana have Trojan companions, Telesto, Calypso, Helene, Polydeuces, parked at Lagrangian points 60 degrees ahead and behind. Those companions add their own gravitational fingerprints. The ring system is a resonance web. Pull one thread, the whole structure shifts. Ring particle composition varies. Saturn's main rings are 95% ice by mass. JWST observations in 2024 confirm highly crystalline water ice in the A ring. Strong absorption at 4.13 microns indicates deuterated water ice, seen earlier by Cassini's VIMS instrument. Carbon compounds exist in trace amounts, 2 to 3%. Aliphatic hydrocarbons suspected in a weak absorption band. Carbon dioxide and carbon monoxide constrained but not confirmed. Silicate material exists, but in small fractions. Cassini's grand finale in 2017 samples, nanograins falling from the rings into Saturn's atmosphere. Silicate to ice ratio between 1 to 11 and 1 to 2. Higher than remote sensing suggests. The falling material is biased towards silicates because nanograins from micrometeoroid impacts are preferentially silicate-rich. The bulk ring composition stays icy. Microwave data identify a unique region in the mid-C ring where particles may have icy mantles over rocky cores. Everywhere else, ice dominates. Jupiter's rings are silicate dust, no ice, too close to the sun and too much radiation. The particles are micron-sized rock fragments from metas, Adrastea, Amalthea, Thebe, reddish color, low albedo, about 0.05. The main ring has boulder-sized clumps a few hundred meters across, confined by Adrastea and Medi. New Horizons imaging in 2007 establishes a lower limit of half a kilometer diameter for embedded moonlets. The rings are extremely tenuous, less than 1/millionth of surface area coverage. Dust density is low. Electromagnetic forces dominate dynamics. Jupiter's magnetic field. Solar radiation pressure, DOS, and various drag forces move particles more than gravity. The rings are ephemeral dust bands, always replenished, always dissipating. Uranus and Neptune rings are dark, silicate and carbonaceous material, some ice mixed in. Spectroscopy struggles to resolve composition at those distances. Uranus particles are coal black, hydrocarbons, tholins, organic gunk. Neptune similar, but dustier. The darkness makes the rings faint, hard to see from Earth. Voyager backlit images reveal them by forward scattered light. Dust scatters light forward better than backward. The rings glow when the sun is behind them, go dark when viewed from Earth. Discovery required occultations and spacecraft flybys. Even now, only the brightest rings, Adams and Leverrier at Neptune, are visible with large telescopes. Uranus rings need Hubble or adaptive optics on Keck. The small body rings, Chariklo, Haumea, Quaoar, are pure occultation discoveries. Direct imaging impossible at their distances and faintness. Stellar occultations provide kilometer-scale resolution. The star blinks. Timing and duration give ring width, position, opacity. Multi-site observations map the ring structure. It's the only way. Ring physics is collision physics. Particles orbit independently but interact constantly. Velocities differ by meters per second, close enough to collide. Impacts at those speeds don't shatter ice, they damp motion. Energy dissipates. Particles that stray above or below the ring plane collide more. Their vertical motion damps first, the ring flattens. Saturn's main rings are 10 meters to 1 kilometer thick. Voyager measures thickness during Saturn equinox, when the rings, edge on, show their profile. 10 to 30 meters in places, incredibly thin for their radial span. Collisions maintain flatness. Particles that stray radially collide too. But radial spreading happens because collisions transfer angular momentum. Particles that gain momentum move outward. Particles that lose it move inward. Over time, the ring spreads. Viscous spreading. The time scale is short, geologically, millions of years. Saturn's rings should have spread into a diffuse cloud. They haven't. Something confines them. Moons. Moons everywhere. Resonances check the spreading. Embedded moonlets stir material, create wakes, clear gaps, reconfine particles. The ring doesn't spread uniformly. It spreads, then gets pushed back. Dynamic equilibrium. Temperature gradients exist. Cassini's CIR's instrument measures ring temperatures. The C ring runs hotter than the A and B rings. More sunlight absorption, because the C ring has more dust and less ice coverage. Dust absorbs better than ice. Temperature affects particle behavior. Warm ice is stickier. Cold ice is brittle. Collisions at different temperatures produce different outcomes. The C ring's higher temperature might help explain its higher silicate abundance. Particles there may be coated differently. Or the formation history differs. The C ring might come from a rocky body. The A and B rings from an icy moon, or micrometeoroid bombardment affects them differently. The C ring and Cassini division have lower optical depth, more exposed surface area per mass, higher neutral absorber abundance, an unidentified UV absorbing contaminant. Exogenous material deposits more efficiently where optical depth is low. The rings record their environment. Density waves propagate through rings, like sound waves through air, but driven by gravity. Moons at certain resonances launch spiral density waves. The wave travels outward or inward, compressing and rarefying ring material. Cassini images show the waves as bright and dark bands spiraling through the rings. The wave properties, wavelength and damping length, depend on ring surface density and velocity dispersion. Measure the waves, derive the ring mass. That's how Cassini estimates ring mass from density waves in the A, B, and C rings. 0.4 Mima's masses, consistent with the direct gravitational measurement during the grand finale. Density waves reveal ring physics. Bending waves, driven by vertical resonances, do the same for ring thickness. The waves are everywhere. Saturn's rings sing with them. Ring rain falls, Saturn's rings shed material constantly. Charged nanograins produced by micrometeoroid impacts and UV irradiation spiral into Saturn along magnetic field lines. Cassini flies through the gap between Saturn and the rings 22 times in 2017, samples the material, silicates, organics, water ice, methane, butane, propane detected. Each second, somewhere between 10 and 99,000 pounds of ring material falls into Saturn. The upper estimate seems too high. The rings don't have enough mass to sustain it long term. Lower estimates more plausible. Nanograin infall, estimated at tens of tons per second. Matches. Ring rain affects Saturn's ionosphere. UV emissions and anomalous patterns at mid-latitudes trace back to incoming ring material. The planet eats its rings. Slowly. Are rings common? Every giant planet in the solar system has them. 4 for 4. Smaller bodies increasingly show rings. 3 confirmed around centaurs and TNOs. 1 probable. Extrapolate. Rings might be common among small bodies in resonance or chaotic orbits. Exoplanet rings remain hypothetical. 2 candidates. HIP 41378F and K2-3 3BE detected by transit photometry. Fomalhaut B, once thought ringed, turned out to be an expanding debris cloud from an asteroid collision. No exoplanet rings confirmed, but the solar system says rings are normal. Where you have a planet, moons, and collisions, rings happen. Maybe temporary, maybe ancient, but they happen. Odd ring facts stack up. Saturn's rings have their own atmosphere. Molecular oxygen produced when UV light splits water ice molecules. Thin, patchy, extends above the ring plane, detected by Cassini. Oxygen escapes or gets ionized and swept into Saturn. The rings glow faintly in UV. Charged particles in the rings respond to Saturn's magnetic field. Electrostatic forces levitate small grains above the ring plane. Spokes appear in the B ring, transient radial features that rotate with the planet's magnetic field, not with Keplerian orbital motion. Charged micron-sized dust lifted by electrostatic repulsion. The spokes appear during certain seasons, disappear during others. The mechanism depends on Saturn's shadow crossing the rings and sunlight angle. Voyager sees them, Cassini sees them, Hubble sees them. They're real and weird. Ring systems precess. Uranus's rings precess under the planet's oblateness. The rings' orbital planes wobble. Neptune's ring arcs precess with Galatea. The whole system rotates. Saturn's rings don't precess much because Saturn is nearly spherical, but perturbations from moons cause local precession. The F ring's orbit precesses differently than the main rings because of Prometheus and Pandora. Every moon adds a twist. Every asymmetry in the planet's gravity adds another. Ring precession rates measure the planet's gravity field. Derive the J2, J4 coefficients. Learn the planet's internal structure. Rings are sensors. They respond to everything. Read the response. Decode the planet. The distant rings, Chariklo, Haumea, Quaoar, sit near the 1 to 3 spin-orbit resonance. Ring particles orbit 3 times per central body rotation. That configuration appears dynamically favorable. Bruno Siccardi's team in October 2025 models the resonance mesh around irregular bodies. First-order and second-order spin-orbit resonances significantly perturb collisional rings. The 1 to 3 resonance excites moderate eccentricities, manageable. The 1 to 2 resonance excites large eccentricities, unstable. Regions inside 1/2 spin-orbit resonance become inhospitable for rings. The 1 to 3 sweet spot explains Chariklo, Haumea, and part of Quaoar. Quaoar also has a ring near the 5 to 7 resonance. Second-order resonance, also stable. The resonance structure determines where rings can survive. Small bodies, triaxial shapes, and mass anomalies create the resonances. Elongation parameter C22 and dipole component mu drive the dynamics, measure the body's shape and rotation. Predict where rings live. The predictions match observations. Chariklo's corrotation points marginally stable. Haumea's largely unstable. Quaoar's safely stable. Rings park where dynamics allow. Everywhere else, they die. Ring science is incomplete. Questions outnumber answers. Why does the atom's ring hold arcs? Why is Quaoar's ring outside the Roche limit? How old are Saturn's rings? What confined Uranus's narrow rings before shepherds were found? What creates the spokes? Why do some small bodies have rings and others don't? How common are rings around exoplanets? Can Earth-like planets have rings? Did Earth ever have rings? A 2023 hypothesis suggests Earth may have had a ring during the Ordovician period, 460 million years ago. Meteorite impact debris. The evidence is indirect, crater locations clustered near the equator. Ring shadow might have caused climate anomalies. Testable but not proven. Rings around terrestrial planets remain speculative. Future missions will answer some questions. No dedicated mission to Uranus or Neptune yet, but proposals exist. NASA's decadal survey prioritizes Uranus. A Uranus orbiter would image the rings at high resolution, measure particle properties, detect shepherd moons, map the ring-moon interactions, determine ring composition, and test age models. Neptune next. A Neptune orbiter would study the arcs, track their evolution, measure Galatea's influence, search for additional moons, and resolve the confinement mystery. Timing uncertain, decades away. In the meantime, ground-based telescopes improve. Adaptive optics get sharper. JWST observes the giant planets in infrared. More occultations of small bodies will reveal more rings. Gaia spacecraft maps, star positions with milliarc-second precision. Predicting occultations gets easier. More campaigns, more discoveries. The small body ring population will grow. Ring analogs exist in astrophysics. Accretion disks around black holes, neutron stars, young stars, protoplanetary disks where planets form, debris disks around mature stars, the physics scales, collisional dynamics, viscous spreading, resonance gaps, shepherding by embedded objects. The same mechanisms operate on vastly different scales. Planetary rings are laboratories. Study them, learn disk physics, apply the lessons to star formation, galaxy dynamics, black hole accretion. Rings teach universal lessons. 2022. JWST images. Neptune. The clearest view of Neptune's rings since Voyager. All 5 main rings visible. The arcs shine. Fainter dust bands between the rings emerge. JWST operates in near infrared. Neptune's methane atmosphere absorbs infrared strongly. The planet darkens. The rings contrast sharply. Background glare drops. The rings stand out. JWST's resolution and sensitivity surpass Hubble. The images stun. Public release. September 2022. Neptune's rings return to prominence after 33 years. The arcs are still there. Still clumpy. Still mysterious. The next generation watches. March 23rd, 2025. Saturn's rings edge onto Earth. Ring plane crossing. The rings vanish from view. Too thin to see edge on. Saturn looks naked. Transient. Last happened 2009. Happens every 15 years as Saturn orbits the Sun and Earth crosses the ring plane. The geometry allows precise thickness measurements. Stars pass behind the rings. Occultations reveal vertical structure. Observers mobilize, amateurs and professionals both. Data floods in. The rings' vertical profile maps out. How thin are they really? Where are they thickest? What's the particle distribution with height? Vertical temperature gradients exist. Measure them. The edge on events are gold mines. Missed opportunities don't return for 15 years. May 6th, 2025. Rings edge on to the Sun. Ring rain rate might spike. Shadow dynamics change. Spokes might appear or vanish. Cassini is gone. Ground-based observers and JWST watch. The rings perform. We record. Haumea's ring discovery reframes Kuiper belt science. If Haumea has rings, others might too. Make, Eris, Gong, Sedna. All large TNOs. All potential ring hosts. Occultation campaigns target them. None found yet. But absence of evidence isn't evidence of absence. The geometries might not align. The rings might be fainter than Haumea's. Patience required. Quaoar's ring broke expectations. The next discovery might break more. The Kuiper belt holds thousands of objects. We've checked dozens. The sample is tiny. Ring science in the outer solar system is in its infancy. Every occultation is a gamble. Sometimes the star blinks and the textbooks rewrite. The rings of Saturn are disappearing. Not in our lifetimes, but they're falling into the planet. Ring rain, viscous spreading, micrometeoroid erosion. Timescales range from 10 million to several hundred million years depending on the model. Hyoto's 2024 work extends the upper limit. Rings might last billions of years if pollution resistance is high, or they might be young and short-lived. We don't know. What we do know is rings aren't permanent. They form, evolve, and die. We live in an era when Saturn has spectacular rings. 1 billion years ago, maybe not. 1 billion years from now, probably not. The rings are a phase, temporary grandeur. We're lucky. Quaoar's ring system expands the mystery. A second inner ring, Q2R, discovered in 2023, closer to Quaoar, also outside the Roche limit. 2 rings in the forbidden zone. Models scramble. Maybe the Roche limit calculation is wrong for small, irregular bodies. Maybe Quaoar's density distribution is unusual. Maybe the rings formed very recently from a satellite breakup and haven't had time to coalesce. Maybe we're witnessing the birth of a moon. If we watch long enough, the rings might collapse into a moonlet, or maybe bouncy particles. Really bouncy, delay aggregation, silicate particles coated with ice, behaving like superballs. The hypothesis is testable. Measure particle collision properties. Lab experiments on ice-coated silicates under vacuum and cold temperatures derive restitution coefficients. Plug into n-body simulations. See if rings stay stable. The work is ongoing, answers pending. Every ring system is a time capsule. The structure records history, collisions, resonances, moon migrations, planet evolution. Decode the structure, read the past. Saturn's rings might be remnants of a Titan-sized moon that ventured too close, or leftover material from Saturn's formation, or a comet that broke apart. Each hypothesis predicts different particle size distributions, compositional gradients, mass distributions. Measure those properties. Test the hypotheses. Cassini provides the data. Analysis continues. Uranus and Neptune rings might be captured comets from the Kuiper belt, or moons shattered by impacts, or primordial. The dark composition suggests comet origin, but the dynamics suggest moon origin. Both might be true. One ring from a moon, another from a comet. Mixed origins, layered history. The small body rings are clearer. Recent impacts, Chariklo, Haumea, Quaoar, all show signs of collisions. Elongated shapes, fast rotations, satellites, rings fit the narrative, but the details matter. When did the collision happen? Thousands of years ago? Millions? The ring evolution rate constrains the event timing. Measure ring properties now, model backward, estimate impact date. The forensic work is just beginning. The Kuiper Airborne Observatory. The plane that discovered Uranus's rings retired in 1995. 48 flights, countless discoveries, replaced by SOFIA, Stratospheric Observatory for Infrared Astronomy, Boeing 747 with a 2.7 meter telescope, operated until 2022. Now retired, infrared astronomy from the stratosphere is on hold. Ground-based telescopes advance, adaptive optics, interferometry, larger mirrors. The extremely large telescope in Chile, 39 meters, under construction. First light expected late 20s. It will resolve ring structures optically, maybe detect rings around exoplanets. Space telescopes improve too. JWST is the flagship. Others planned. Roman Space Telescope, Nancy Grace Roman, launching late 20s. Wide field infrared, might catch exoplanet rings in transit. HabEx and LUVOIR, proposed missions, would directly image exoplanets. See rings directly, funding uncertain, timelines stretch, but the capability is coming. Exoplanet rings will be found, probably common, certainly diverse. Rings matter because they're beautiful and because they're physics. Every ring is a controlled experiment. Gravity, collisions, electromagnetism, radiation pressure, all acting together. Measure the outcome, test the theories, particle dynamics, orbital mechanics, resonance theory, collisional physics, electromagnetic interactions. Rings are testbeds. They operate in parameter regimes accessible to models. Not too big, not too small, not too fast, not too slow, just right. You can simulate a ring system on a computer, billions of particles. Integrate their orbits, include collisions, add moons, watch structure emerge, compare to observations, iterate. The simulations improve, the understanding deepens, rings connect theory to reality. No rings, no test, no progress. The last revelation comes from soil cores. Boundary markers dug from ancient orbits, mass graves that match saga losses, or in this case, a stellar occultation measurement from 2023 confirming Quaoar's second ring with an optical depth variation that implies recent formation. Cross-checked with historical occultation data showing the ring wasn't there in 1984, meaning this ring is younger than 40 years old, possibly formed from a satellite collision we didn't see because nobody was watching. And now we stand at the edge of a discovery wave where small bodies reveal rings we never predicted, in places theory said were impossible, teaching us that rings don't follow our rules, they follow theirs, and the cosmos writes its own manual while we scramble to read it. Every ring around every world is temporary. Borrowed time, dust and ice spinning in sunlight. We look up, see structure, assume permanence. The rings know better. They orbit, collide, spread, fall, and vanish. What remains is data, images, measurements, and the understanding that beauty is dynamic. The rings aren't frozen sculptures. They're rivers of particles in constant motion, shaped by forces we barely grasp, surviving against entropy through mechanisms we're still mapping. Each new discovery reminds us the universe is richer than our models, stranger than our theories, and full of rings where rings shouldn't be. The small asteroid Chariklo wears 2. The elongated dwarf planet Haumea spins with 1. The distant Quaoar defies physics with 2 in the wrong place. And Saturn keeps shining, pouring ice into space, feeding a ring that may or may not be older than dinosaurs, younger than mountains, or exactly as old as the moment we looked up and wondered why.